Hello everyone. This is the video lecture for the topic Context-Free Grammars. This is from the first unit of Principles of Programming Languages. Context-free grammars are developed by Noam Chomsky in the middle of 1950s. These are the grammars which are used to generate the languages and the language statements. It meant to describe the syntax of natural languages. It defines a class of language called context-free languages. These grammars will have the set of rules. A rule has a left-hand side and the right-hand side, and it consists of terminal and non-terminal symbols. BNF, it is one of the normal form invented by the John Backus to describe the syntax of some particular programming language, which is equivalent to the context-free grammars. An abstraction can have more than one right-hand side. Abstractions are used to represent classes of syntactic structures. They act like syntactic variables. They are also called non-terminal symbols or just non-terminals. In the rules, we have terminal symbols and non-terminal symbols. Non-terminals are nothing but variables. Terminals are lexemes or tokens. In rule, the left-hand side, which is the left-hand side, will have the non-terminal, and the right-hand side will have the terminal as well as non-terminal. Examples of BNF rules. It will be in the form like identifier list implies identifier or identifier list. Like if statement implies if, logic expression, then statement. BNF is the grammar. It is a finite non-empty set of rules. An abstraction can have more than one right-hand side. Syntactic lists are described in BNF using recursion. And then derivation. It is a repeated application of rules starting with the start symbol and ending with the sentence. In derivation, we will substitute the appropriate values or statements in the rules, and finally we will generate the sentence. An example grammar. This is a grammar. Each and every line is called as rules. Program tends to statements. Statements imply statement, sequence of statements. Statement implies variable, which is equal to expression. Variable implies A or B or C or D. Then expression implies term plus term or term minus term. Term implies variable or constant. And now we can see an example derivation. So derivation means substituting the values from the set of given rules, and we will start from the starting grammar. Program implies statements. Then statement. We can substitute. Now we are substituting another one rule, that is statement implies variable equal to expression. Now we have substituted for the second line statement, we have substituted in the third line variable equal to expression. In the next line we are substituting A for variable, A equal to expression. In the next line we are substituting term plus term for the previous right hand side expression. So A equal to term plus term. In the next line we are substituting B variable for the term. These are substitutions will be taken from the grammar. So we are getting A equal to variable plus term. In the next term we are substituting B for variable. So we are getting A equal to B plus term. In next line we are substituting constant for term. So in the derivation, one by one each substitutions will be performed in individual steps, and finally we are getting one programming statement A equal to B plus constant. So in derivation, every string of symbols is in a derivation is a sentential form. A sentence is a sentential form that has only terminal symbols. A leftmost derivation is one in which the leftmost non-terminal in each sentential form is the one that is expanded. A derivation may be neither leftmost nor rightmost. So this is a tree-like structure of derivation. So first of all, program we have substituted statements for program, then we have substituted single statement for statements, then statements will be replaced by variable equal to expression, then we are substituting a for variable, then term plus term will be for expression we are expanding expression by term plus term, then we are substituting variable for term, and we are substituting constant for the another term, then finally we are substituting b for variable, and finally we are getting the statement a equal to b plus constant. So we can also represent the derivation in a form of a tree. This tree is called as parse tree. Ambiguity in grammar. For a same derivation, if we get two different parse tree, if you are able to get two different parse trees for the derivation, this grammar is called as ambiguous grammar. We will tell there is an ambiguity in grammar. So this is an example. So for the same derivation, this is one simple grammar, and we are deriving the grammar, and finally we are getting constant minus constant divided by constant. But with the same grammar, for the same derivation, it is possible to draw two different structure of the parse tree. So we can tell this is the ambiguous grammar. There is ambiguity in the grammar. An unambiguous expression grammar means there is a unique parse tree can only be drawn for the particular derivation. Such if this condition attains, this grammar is called as unambiguous grammar. Operator precedence. If we use the parse tree to indicate precedence levels of the operator, we cannot have ambiguity. Associative of operators. Operator associativity can also be indicated by the grammar. Extended BNF. There are some more options are available in the extended BNF than the BNF. Like optional parts are placed in the brackets. For example, procedure call implies IDENT. Optional parts are represented inside the bracket. Alternative parts of right hand side are placed inside parentheses and separated through the vertical bars. Repetitions are placed inside the curly braces. These features are available in the extended BNF like this. And recent variations in eBNF. Alternate right hand side are put on separate lines. Use of colon instead of this particular symbol. Use of opt for optional parts. Use of one-off for choices. These are available in eBNF. So that's all about the topic. Thank you.